NASA has received transmissions from interstellar object 3I Atlas, confirming what we all feared.
Astronomers just confirmed the heaviest interstellar visitor ever found, and nothing about it makes sense. In July 2025, telescopes spotted 3I Atlas, the third object ever detected entering our solar system from beyond. At first, it seemed like just another cosmic wanderer passing through our neighborhood, but as data rolled in from observatories worldwide, scientists realized they were dealing with something unprecedented, a comet weighing at least 33 billion tons, the most massive interstellar object on record, breaking every rule about how these visitors should behave. The Atlas telescope in Chile first caught the anomaly, a blur moving impossibly fast on a hyperbolic trajectory, the signature of an object not bound to our sun. It came from interstellar space, joining only Oumuamua and Borisov in that exclusive club. But 3I Atlas was about to prove itself unlike anything before it. Early measurements showed a nucleus roughly 5.6 kilometers across, large but not unprecedented. Standard comet science says that size should produce predictable behavior. As comets approach the sun, solar radiation warms their surfaces, causing frozen gases to sublimate directly from solid to vapor. Ice turns to gas, creating jets that act like tiny thrusters, pushing the object off course. This phenomenon, called non-gravitational acceleration, is textbook physics. Every active comet experiences it. The escaping gases create visible comas and tails, while altering the object's trajectory beyond simple gravitational influence. Except 3I Atlas doesn't follow the script. Despite clear evidence of gas and dust erupting from its surface, a visible coma streaming into space, the comet's path barely deviated from what pure gravity alone would produce. Tracking data from 227 observatories worldwide, collected between May and September 2025, revealed something impossible. Non-gravitational acceleration measuring less than 15 meters per day squared. For a comet this visibly active, that number should be exponentially higher. It's like watching a rocket engine fire, while the rocket itself barely moves. The only explanation? Mass. This thing has to be absurdly, anomalously heavy. When scientists ran the numbers, balancing observed outgassing against minimal trajectory change, they arrived at a stunning conclusion. 3I Atlas must weigh at least 33 billion tons. That's several orders of magnitude more massive than Borisov, and vastly heavier than Oumuamua. To put that in perspective, this is heavier than entire mountains on Earth, packed into a comet nucleus just a few kilometers across. Something about its composition is fundamentally different from what astronomers expected. Most comets are fluffy mixtures of water ice, frozen gases like carbon monoxide and methane, rocky dust, and organic compounds, materials giving them relatively low density. But 3I Atlas resists forces like it's made of something far denser. Either it's hiding a much larger nucleus beneath its glowing coma, or it's packed with rock and metal in proportions that shouldn't exist in a comet-like object. Why does that matter? Because composition reveals origin. Comets carry chemical fingerprints of where they formed, the temperature, pressure, and materials available in their birth star system during planet formation. An interstellar comet is essentially a messenger from an alien solar system, carrying information encoded in its atoms about conditions that existed billions of years ago, light years away. The James Webb Space Telescope captured something genuinely strange. Spectroscopic data revealed unusually high levels of carbon dioxide relative to water vapor. This object ranks among the most carbon dioxide-rich comets ever studied, flipping typical comet chemistry on its head. Most comets are water-dominated, with carbon dioxide playing a supporting role. 3. Atlas reverses that expectation in ways suggesting formation conditions radically different from what shaped icy bodies in our solar system. Ultraviolet observations added another mystery. The comet started venting water vapor at distances where most comets remain completely dormant, their surfaces still too cold for water ice to sublimate efficiently. This early activation suggests either a fundamentally different ice structure or a surface composition responding to solar radiation in ways we've never encountered before. If you're finding this as mind-blowing as I am, hit that subscribe button and turn on notifications so you don't miss what happens next with this cosmic mystery. And if you're enjoying the video, smash that like button. It really helps us bring you more deep dives into the strangest discoveries in space. Then came the polarization data. When sunlight bounces off dust particles in a comet's coma, it becomes partially polarized in patterns patterns acting like fingerprints. Astronomers compared the polarization signature of 3I Atlas against extensive libraries of data from solar system comets and asteroids. They didn't find a match. The pattern showed characteristics distinct from both groups, suggesting dust grains with a different structure or mineral composition than anything forming in our local cosmic environment. And here's where it gets genuinely unsettling. Early spectroscopic analysis hinted at nickel in the coma, without the corresponding iron signature that universally accompanies it in natural cosmic processes. In universal chemistry, nickel and iron are essentially married, forged together in stellar cores during supernova explosions, ejected together, mixed into clouds that eventually form new planetary systems. Finding one without the other would be extraordinary, pointing toward either an incredibly rare formation process or some selective vaporization mechanism. The data remains unconfirmed and could be an instrumental artifact, but if it holds up, that's yet another impossibility. Harvard astronomer Avi Loeb isn't pulling punches about what this might mean. If the mass calculations and compositional anomalies hold up, he argues, conventional natural explanations may fall short. Loeb previously suggested Oumuamua's strange acceleration could indicate artificial origin, essentially proposing it might be an alien probe. That claim made him simultaneously famous and controversial among colleagues who felt he was jumping to extraordinary conclusions without exhausting ordinary explanations first. Now Loeb is eyeing 3I Atlas with similar skepticism. When anomalies pile up this high, the impossible mass, bizarre chemistry, unusual polarization, potential nickel without iron signature, he asks a provocative question. At what point do we acknowledge that natural explanations aren't adequately accounting for what we're observing? NASA planetary scientist Tom Statler offers a measured counterpoint. When you strip away interpretive layers, it looks and acts like a comet. The outgassing is real. The coma is visible through multiple instruments. The trajectory fits the profile of a natural object responding to solar heating, just with some parameters pushed to extremes. Yes, it's heavier than expected. Yes, the chemistry is unusual, but unusual doesn't mean impossible, and it doesn't mean we need to invoke anything beyond natural astrophysical processes. With only 3 interstellar objects ever confirmed, we simply don't have the statistical foundation to define what's normal. Let's consider what we know about interstellar visitors. Oumuamua arrived first in October 2017 and immediately defied expectations. Observations revealed an extremely elongated shape, tumbling in a complex pattern. Most strikingly, it showed significant non-gravitational acceleration despite no visible outgassing. No coma formed, no tail appeared. It looked like an asteroid, yet something was pushing it off a purely gravitational path. That discrepancy sparked years of debate, with explanations ranging from hidden outgassing vents to more exotic proposals about artificial origin. Borisov provided stark contrast when it arrived in August 2019. It looked and acted exactly like a textbook comet. A clear coma surrounded the nucleus. A classic tail streamed behind it. Spectroscopic observations revealed chemistry remarkably similar to comets in our solar system. Its non-gravitational acceleration matched predictions perfectly. Borisov reassured astronomers that interstellar comets could behave in familiar, predictable ways. Then 3I Atlas arrived and shattered that comfortable assumption. It shows clear comet characteristics, visible gas and dust activity creating a detectable coma, but its nucleus resists forces that should be dramatically altering its trajectory. The minimal non-gravitational acceleration implies a mass of at least 33 billion tons. That makes it the largest and by far the heaviest of the 3 confirmed interstellar objects. Its chemistry stands apart, with that extreme carbon dioxide to water ratio placing it at the far edge of known comet compositions. Here's the problem keeping planetary scientists awake. Theoretical models predict that interstellar space should be filled predominantly with small fragments, debris from planetary formation, material ejected during gravitational interactions, fragments from collisions. The physics strongly favors smaller objects. For every large body expelled from a planetary system, hundreds or thousands of smaller fragments should follow. Yet the reality looks completely different. Oumuamua measured at least several hundred meters. Borisov spanned roughly a kilometer. 3I Atlas exceeds 5 kilometers and weighs at least 33 billion tons. All 3 fall into the category of relatively large objects. The odds of detecting 3 such massive bodies in sequence while missing countless smaller fragments, vanishingly small. It's like randomly sampling fish from the ocean and pulling out only great white sharks. Several explanations could account for this discrepancy. The simplest is observational bias. Larger objects are dramatically easier to spot. They reflect more sunlight, produce more spectacular comas, leave clearer signatures in automated sky surveys. Smaller fragments might be passing through regularly clearly, but remaining invisible to our instruments, too faint to trigger detection algorithms. If this is correct, the true population of small interstellar objects could be vast, but effectively invisible to current capabilities. Another more troubling possibility is that theoretical models themselves are fundamentally wrong about size distribution. Perhaps ejection processes don't favor small fragments as strongly as predicted. Maybe gravitational dynamics preferentially eject larger bodies. If large comets and asteroids are genuinely more common in interstellar space than theory suggests, then detecting them first wouldn't be surprising at all. The Vera C. Rubin Observatory offers humanity's best hope of resolving these questions through sheer statistical power. Its unprecedented imaging capabilities make it uniquely suited to detecting faint, fast-moving objects that previous telescopes would miss entirely. Over coming years, as it conducts continuous sky surveys, it's expected to detect many more interstellar visitors, finally providing the robust statistical sample needed to definitively answer fundamental questions. As 3I Atlas continues its approach toward the Sun, high-resolution imaging scheduled for early October may reveal crucial details of the nucleus hidden beneath the coma. Re-emergence from solar conjunction in December will offer fresh opportunities to study its behavior as solar heating intensifies. This truly is a one-time opportunity. @ Meta. Pause. Sex 0.05. Once 3I Atlas completes its flyby and exits the solar system, it's gone forever, carrying all its secrets back into the void between stars. Sometimes the most scientifically important discoveries are the objects that stubbornly refuse to behave as expected, that break rules we thought were fundamental. 3I Atlas is proving to be exactly that kind of object, a massive anomaly, challenging everything astronomers thought they understood about interstellar space. How does something this impossibly heavy slip into our solar system while defying basic comet physics? What kind of star system could produce an object this dense and chemically bizarre? And perhaps most unsettling, if this is what we're finding with only 3 confirmed detections, what else is out there in the darkness between stars that we haven't yet developed the tools to see? Will the next interstellar object finally provide clear answers to these mounting questions? Or will it simply prove that the universe is far stranger, far more diverse, and far less predictable than our most ambitious models imagine? One thing is becoming increasingly certain as the data accumulates: we're not ready for what's coming next. If you want to stay updated on 3I Atlas and the next interstellar visitors that will inevitably reshape our understanding of the cosmos, make sure you're subscribed to this channel. Drop a like if this blew your mind, and let me know in the comments what you think is really going on with this mysterious object. Thanks for watching, and I'll see you in the next one.